Uh, Good afternoon, students. Let us begin today's discussion from the same point where we left off. So, in the last class, we are talking about types of different liquid crystals, and we mostly focused on the various types of liquid crystalline phases. Now, today we take one step forward and we ask questions about the building blocks in chemical sense, the building blocks that will give rise to the particular kind of liquid crystalline phases that we have discussed. So in today's discussion we mostly focus on molecular structure of liquid crystalline materials, exact molecular structure, and how those structures can be tailored to generate specific liquid crystalline properties. So for example, if I want to have a liquid crystal which in a specific temperature range, then what kind of structure I should choose, how can I tailor this particular molecular structure. So there are enormous number of liquid crystalline materials available now. They have been prepared and many of them are very similar in nature, and each one of these liquid crystalline materials they have these distinct properties, okay, though their structures are very similar, and that happens because of the very structural perspectives of that particular material that concludes into the phases and phase morphology and particular values of, say, physical quantities like melting point, transition temperature, and so on. So additionally, the combination of these structural properties only is very important if we consider a specific kind of application. So if I want to design a liquid crystal for a very specific application, these particular structural properties or design, so to say, plays a very important role. Okay, so in today's class, our main goal is to take into account this huge number of organic compounds that have been prepared, and we let us just focus mostly on rod-like liquid crystals. We call them calamatic liquid crystals, right? In the last class, we defined these particular structures of liquid crystals who have a very specific shape like a rod, and we call them calamatic liquid crystals. So we will focus on those liquid crystals to begin with, and we will think about how they can possibly be prepared and how they can give rise to a very particular phase, okay, so that they can be suitable for a very particular application. So to begin with, I must say that all scientists that are working in this particular field, be they chemists or physicists, mathematicians, engineers, this is a very interdisciplinary field, so electronics and biologists as well, so they all require at least to have a basic understanding of these relationships, that how the structure controls the property, and that is what is basically the basic technical term that we are going to discuss today is the structure property relation. So structure property relation is basically the thing that is our focus today, right? So if someone asks you that what is a structure property relationship, that simply means that how the specific structure of a liquid crystal gives rise to extremely interesting aspect of this particular behavior of a liquid crystal. So if we think about the industrial application, the nematic liquid crystals, that phase is technologically the most important compared to the other different liquid crystalline phases, because nematic liquid crystals basically found maximum application in liquid crystal displays. We'll talk about them later. So but if we just talk about the value, right, the world market of liquid crystalline displays, that is continuing to expand very strongly, and it's billions per year, which accounts for a large proportion of the total number of displays that we have. So liquid crystal displays are expected to satisfy the demand of medium size displays, and on the other hand, smectic liquid crystalline phases, though they have found very little commercially successful applications, however they are also finding, like chiral smectic C liquid crystals are finding their application in display industry gradually. So accordingly, the structure property relations that you want to make a particular kind of smectic chiral smectic C kind of a liquid crystal, or a particular kind of nematic liquid crystal, that needs you to understand this structure property relations very clearly. Okay, so what are the questions that we want to focus on today, or what are the questions that we are addressing today? That what type of structural units, right, or combination of structural units will allow the generation of, say, the nematic phase. So we are talking about calamatic liquid crystals, and nematic is one of the most important phases with these calamatic liquid crystals. So what kind of structural units contribute to that, or say how do these differ from those that are required for a smectic phase, say, right? How do the structural features vary from one type of smectic phase to another type of smectic phase? The structure or the structural units, how they differ. What structural features are responsible for generation of a smectic phase which is tilted smectic, right? So like the question like this, that how do the structural features affect the physical property of liquid crystalline materials? What predictive powers does the synthetic chemist, if I am trying to predict something, how can I accurately synthesize a material after I predict that this kind of a unit, if we combine them properly, then they will give rise to this kind of a property. Okay, so that is basically the goal of today's class. So before attempting to answer all these questions, let us just focus on the very general structure or template of calamatic liquid crystal. So this is a general structural template of a calamatic liquid crystal. Okay, so this clearly looks like a rod shaped thing, right? So including this kind of structure includes both smectic and nematic phases, because both of them are rod shaped, as you know, right? So what are these different parts that we are seeing here? Let me just explain each of these parts that we are seeing here, each of these blocks or units, so to say, that we are seeing here. What are these things like A, B? What are these things? So A and B, okay, are called the core units. So A and B are called the core units. Okay, core units. They constitute the core units. So A and B are sometimes linked by a linking group. So this is the linking group. Okay, linking group. So they are sometimes linked by a linking group, sometimes they are directly connected, sometimes, more often basically, they are directly connected. There is no why, they are directly connected. Similarly, the terminal chains that you can see, this R and R prime, these are basically the terminal chains. So core is supposed to be the solid part of it that will give it a stick-like structure. On the other hand, R and R prime are basically the flexible tails. Okay, so they are these terminal chains, and they can be linked to the core by these groups X and Z that we have here. So X and Z, these are the groups that are the linking groups in the terminal chains, or they can be directly connected to A and B as well. Okay, so the units that are used in this general structure, their combination determine the type of the liquid crystal that exhibit a particular property. Here we also have M and N. I just forgot to talk about them. So M and N are basically called lateral substituents. So let me just write it. They are called lateral substituents. Okay. So these M and N are usually not part of the liquid crystalline materials. That it's not that they are basically essential to show liquid crystalline properties, but they are often used to modify the morphology and physical properties so that you can apply it to for a very particular application. So these basically generate these enhanced controls in your hand so that you can control the physical properties a little bit more. So this is basically the structural basic structural parts of a liquid crystal material, calamatic liquid crystalline materials. Now let me just one by one say what do I mean by this A and B. What do they chemically signify? What are these different parts, A and B and R prime? So let us just talk about them one by one. So before I go to that, all of these are organic molecules, right? So let me just quickly remind you some basic what should I say, terminology about organic molecules. How do we name that? So usually when we have this rings kind of a structure, these rings, benzene ring or any other kind of rings that you see in organic molecules, they are named, or their nomenclature has a very particular way of doing it. So I am sure that you are familiar with these words, but let me just quickly remind you: ortho, meta and para. So if you are counting from here, then if it is this position is called ortho, this is called meta, this is called para. And we also name these things, like if I have a substitution at B, then we call it 1,2 or 1,3 or 1,4, like that we name these organic materials. So I just ask you to quickly revisit these things if you forgot about these things, but I'm sure that you know most of these things. So let us just go into a little bit deeper and talk about our core. So core of these liquid crystalline materials are basically these linearly linked ring systems. Okay, this is a very, very common structure. This is the most often common structure. They will be in form of aromatic rings. So what are these things that I have here? I have 1,4-phenyl or 2,4-pyrimidinial or 2,6-naphthyl. So these are the three very common cores that you have. Okay, so they are in general aromatic, and they are basically signifying those A and B that I wrote down there. Okay, so but beyond this, you can also have different kind of like alicyclic materials as well. So sometimes trans A1,4 cyclohexyl is one of the very common cores that are used. So you can just look for it, that what kind of different cores can you use to make this liquid crystalline materials. But these are the common structures that we have. Okay, so here one important thing to mention would be that usually the two rings that are giving rise to liquid crystalline phases, there I need these two rings. Okay, that is the most common part. But there are some rare example where you have this acyclic materials. That means where you don't have any cycles present in general or in normally present in the structure, but hydrogen bonding is responsible for giving an elongated unit at the rigid central core. So let me just show you one example. This is a very, very rare liquid crystalline material where here you can see the material itself. If you look into it, the material itself does not have any cyclic structure in it, right? Not aromatic and not having any cyclic structure of any other kind as well. Okay, so that is not the core. The core is not made of that. So let us just focus on the top material for now. So here you can see that the material itself is basically up to this. Okay, this is the molecule we are talking about. Okay, this is the molecule that we are talking about. And a similar molecule is sitting at its side. A similar molecule is sitting at its side. Okay, so and then both these materials have these two flexible terminal chains. The central ring is generated by intermolecular hydrogen bonding, and this linear rigid unit is significantly extended to as if a trans-substituted unit, which is like a core structure, which has a cyclic core structure, but it is not. It is just made of hydrogen bonds. So similar structures are also there in the example below, where you have liquid crystalline phase generated, but the core itself is not cyclic or have any rings to begin with. But in general, in the most common examples, that is the structure that we have. So let us just talk, as we are talking about the common examples of liquid crystal, let us just take some very basic examples of liquid crystals, name of the liquid crystal materials which are most commonly used in labs. So the first example is p-azoxyanisole, PAA, p-azoxyanisole. Here you see a similar kind of structure that I have just described. Here you see two benzene rings and they are connected, and on the both side you have these tails where some CH3 are just hanging around. Okay, so this is p-azoxyanisole, and it is called a nematogen. Let me just write this term down here. It's called nematogen. Okay, and as the name suggests, this word simply means that they give rise to nematic type mesophase. They are capable of giving rise to nematic type mesophase in a particular temperature region. So what is that particular temperature region? For PA, it is between 116 degrees centigrade to 135 degrees centigrade. So 116 to 135 degrees centigrade at atmospheric pressure, this material behaves like a nematic state. It has a nematic state. Okay. Another example that is most commonly used is has a structure like this. Okay. Here also you see that this tail is hanging around CH2, 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 CH3. This is the R that we are talking about in the basic structure, R or R prime. That is the flexible tail that hangs around from the rigid core. So this is the rigid core, right? You have two rings connected by, this is your Y, this is your R, and this is your R prime. Okay. So this is the structure that we have. This material is called MBBA. Sorry, I wrote it wrong. It's called MBBA, N-methoxybenzylidene p-butyl-aniline. Okay, so N-methoxybenzylidene p-butyl-aniline. Okay, so that is the material that you have. We commonly call it MBBA, and MBBA has a nematic form between this is another very common nematogen, and this is used in laboratories to demonstrate liquid crystalline experiments for students. Most commonly, if you Google and look for YouTube videos where people are performing experiments with liquid crystalline molecules in their labs, then most of the time they are using MBBA, and because this gives its liquid crystalline nematic phase between 20 degrees centigrade to 47 degrees centigrade. So this is the range. This is the range between which it attains nematic form, and thus it is much easier for experimentation in labs. Okay, but the problem with this particular material is its chemical stability. From that perspective, PAA is more generally used. So these are the most common example of liquid crystalline materials. But in a broad class, if you think of the basic structure that we have, so that basically resembles with the structure that I have just demonstrated 2 slides back. So what are the common R and X and R prime? So sorry, this is your Y basically. Sorry, that is the connecting part. So you have R, that is the tail on one side, then you have the benzene ring, you have some kind of a ring structure here. Okay, some kind of a ring structure here. Then that ring structure gets connected to another ring structure via a particular group. Okay, any kind of a ring structure, and this side you have R prime, this side you have R. So this is the general structure. This is written as X here. In the previous diagram, this same thing was called Y. So these are the common linking groups, so to say. Okay, the linking groups that links the two aromatic rings to form the solid core. On the both sides you have this hanging flexible chains, and they have a very significant role as well. The chains have a very significant role as well. We will now discuss about it, because the core is more or less what we understood, that how the core will look like and how they will be linked, by what kind of groups they could be linked. So all these groups that you see here are the most common links that can be formed between the two rings A and B in our first picture. Okay, and R or R prime are usually this straight alkyl or alkoxy chains. So you have these chains which are hanging freely on both ends. Okay, sometimes in case of these materials, you have one terminal unit which might have a small polar substituent, like you have fluorine or bromine or chlorine, this kind of a polar material CN. They can be sitting on one end. Occasionally the terminal chains, sometimes they are branched as well, and sometimes one branch is polar, another one is non-polar. So these kind of different structures you can have. Okay, so this tails that I have on both sides basically are also an important part, because we talked about the core. Now let us talk about the tails that we have on the both sides. So they are also a very important part in deciding that it is going to be in a nematic phase or in a smectic phase, because the structure wise, if you see structure wise, so the so-called nematogens and smectogens, that is the molecules that can behave like nematics in a particular temperature region, or smectics, their structures are both same. They are all calamatic or rod-like, right? So what will decide that which material will behave like a nematic or which material will behave like a smectic? Sometimes, often, it can also happen that they behave like both, because it sometimes happens that in crystalline you have this perfect order present, and then you have smectics where the order is a little bit disturbed, but the positional as well as orientation order is present, and that is our smectics. Then you have nematics where it is completely destroyed, the positional order, but the orientational order is still there, and then finally you are in the isotropic phase. So some materials are there which can behave as both smectic and nematics, but still and that is why sometimes it is difficult to be very rigid and draw a very rigid line and say that these structural features will give rise to nematic phase and these will give rise to smectic phase, but still, because of the importance of nematic phase in the technological industry, it is people try to figure out that what kind of material will behave like nematogens and which will behave like smectics. So let us talk about that. And here the tails have a very, very important role to play. Okay, the tails have a very, very important role to play. So if you remember how the smectic phases look like, they most of the time they were soap-like, right? And they were forming this lamellar structure. They were forming this series of lamina inside the material, and they were having this lamellar packing kind of thing, right? So the most striking difference between these two phases, nematic and smectic, is that lamellar packing. So if the structure is such that it does not encourage such layer-like arrangement, okay, then nematic phase is more likely to generate. And there, this common generalization is that the nematic phase is facilitated by the relatively short chains. So if you have these short tails, longer ones, they tend to stabilize and give rise to lamellar arrangement. So just to quickly remind you the lamellar arrangement, I mean that this particular material having arrangement like this, right, where they just have this particular stacked kind of an arrangement. And if you have long tails, if that particular material has long tails, then that basically stabilizes this kind of a lamellar arrangement of molecules. Okay, short tails does not. Short tails does not encourage that, and so thus, if you have a material with which achieved by keeping the core as well as the tail of almost the same length, that is the terminal chains are not very long, then basically that most of the time gives rise to nematic phases. If you have long chains or long terminal chains, that gives rise to this smectic phases. Okay, so that is one of the most striking difference between them. And there is also a ranking of that is completely based on experiments, that is not very much physically established, but there is a ranking of which group, presence of which group has a relative efficiency in forming nematic phase generation. Okay, which terminal units, if they are present, then the relative efficiency of nematic phase generation is high. So there is kind of a ranking where ranking goes like this. So like this kind of a group has a more efficiency to give a nematic phase compared to CN, compared to OCH3. Okay, so this is just based on experiments though, but still. So chlorine and bromine. So this is how the preference goes. Okay, then fluorine, H, and CH3 lies somewhere here. Okay, and so on. So this is kind of the relative efficiency of nematic phase generation if you consider the terminal units present in that particular material. Okay. So I hope this particular distinction between nematogens and spectrogens, though that line cannot be drawn very strongly, but that part is more or less clear to you. Now let us talk about another very important property that is associated with this nematic phase, and that is the nematic phase stability. Okay, so the term nematic phase stability actually refers to the upper temperature limit Tni, that is T nematic to isotropic. Okay, that is up to the temperature up to which the nematic phase exists. So it's the temperature limit up to the nematic phase exists, and the term nematic range means the temperature range over which the nematic phase exists. So this is just the highest temperature up to which you can have nematic phase, and this is the range, the entire temperature range between which you can have these materials in nematic phase. Okay, so these are two important measures of seeing that how good a particular nematogen is, how good your nematic materials are for industry application. So here one striking difference I must point out is that in many materials, the tendency of many materials is to supercool before they recrystallize, and that enables the nematic phase to be exhibited as a metastable state, okay, below melting point. So we will talk about these different kinds that we are talking about, that is based on the phase stability and melting point of the material, and along in that line the material is the particular materials are classified in two classes, monotropic and enantiotropic. So let us just talk about these two types of liquid crystals as well with some examples. So for example, let us look at these compounds that we have. Let us just call the first compound number 1, 2, 3 and 4. Okay, so let me just these are all nematogenic materials. These are all materials that give rise to nematic liquid crystals, and they are used in liquid crystalline displays. So say here I have some notations written there, right? So you can see that here it's written that C24N35I. Okay, what does it mean? So if with every liquid crystal you see that I have certain kind of those numbers written. Let us just try to understand this, and from that we will understand what is monotropic and what is enantiotropic material. So for example, this particular material for compound number 1, it melts at 24 degrees centigrade, okay, and has a nematic phase stability of 35 degrees centigrade. Remember that nematic phase stability tells you about the upper temperature limit up to which you can have nematic phase present. So that means if the material melts, that is before that it is crystal. So C signifies crystal. Okay. So at 24 degrees centigrade it melts and it remains liquid at nematic phase till 35 degrees. So what is the nematic range? This minus this, that means 11 degrees of centigrade is its nematic range. Okay. So here you can see this kind of material where the nematic phase stability is higher than the melting point, and that is the common thing to think about, is called enantiotropic material. So this particular kind of material that we have where it melts and the melting temperature is less than the nematic phase stability, then it is called enantiotropic. Just let me write it down once again. Enantiotropic material. Okay. So on the other hand, let us look at this compound, compound 3. Okay. So compound 3 melts to an isotropic liquid directly at to an isotropic liquid at 48 degrees centigrade. Okay. And the nematic phase, here you can see the nematic phase is lasts up to 16.5 degrees centigrade. So that means the nematic phase has a phase stability of 16.5 degrees centigrade. So how can you see the nematic phase, right? How can you see the nematic phase if it is still at a crystalline phase? Because it melts at 48 degrees centigrade. Do you understand what I am saying? So the compound melts at 48 degrees centigrade, and the nematic phase, how can it be formed? It can only be formed on supercooling the liquid. So supercooling means that you make the liquid remain at liquid phase below its melting point, right? So that is what supercooling means. So supercooling the liquid, and it has a phase stability of 16.5 degrees centigrade. Okay. So consequently, there is no enantiotropic nematic range here. So there is no range of this material that it remains even higher than the melting point, it remains nematic. No, if you want to see the liquid crystalline phase in this particular material, you have to supercool it. So you have to supercool. Okay. Have to. So this kind of materials are called monotropic. They are also industrially used, by the way. Okay. So they are not like completely useless. They are used in industry in making liquid crystalline displays. All of these materials are used basically. So so on the other hand, finally this compound 4, let us look at this compound 4. Okay. So compound 4 is an interesting material. It melts at a relatively higher temperature. So this is the melting point. I guess by now you understand crystal. After that, the temperature that is written, say here or here, this is the point where the solid becomes liquid. Okay. So this is the melting point. This is the notation. This is how the notation is written. So crystal becomes liquid, that is crystal loses its form, that means it melts at a relatively high temperature of 75 degrees centigrade, right? And it does not supercool sufficiently to allow the nematic phase to be generated because it is this temperature is quite high. Okay. Now, accordingly, a nematic phase stability is determined by formulating mixture with a host material. Okay. So we mix a different material to this particular material, and I try to extrapolate this value of phase stability in a certain way so that you get to see this liquid crystalline phase. Okay. So liquid crystalline phases are often denoted in a standard format with monotropic phase if they have these round brackets. If they have these round brackets, that is the first brackets, then that means they have a monotropic phase, and that is achievable by supercooling it. Okay. And if that is virtual, that means if you do some special experiments, if you do some mixing or you do use some host material, you formulate some mixtures, that means it's a virtual value when you use these third brackets. That means if you experiment on it, do some tricks, then you can make a nematic out of it which has a stability of 22 degrees centigrade. Okay, so this third brackets means it's a virtual value. It's a virtual value which can be achieved not by the natural material but by using some tricks, doing some special experiments. Okay, if it is written in third brackets. So here on top I have another material, compound 2, which we have not discussed about much. So compound 2 is basically not a nematogen. Okay, nematogens are basically those materials which give rise directly to liquid crystalline phases in a temperature range. Okay, but there are other compounds like compound 2 which exhibit nematic phase at a temperature above those for smectic phases. Okay, so smectic phases are also seen, and after that nematic phase is seen once the positional order is also lost. So here you can see in this particular material we have this long numbers and letters written here, and that signifies what? So one by one you can, if you understood by now, you can see, you can just explain it, that the crystal melts at 56 degrees centigrade. Then after that, once it melts, after that you have a smectic C. The smectic C loses its behavior and becomes a smectic A at 105.5. Then smectic A becomes nematic by losing the positional order at 131. Nematic stability remains till 136, and after that it is isotropic. So this is the standard notation. I hope you understood this. Try to go through it, okay, so that you try to explain and go through it, that how these notations are done and how these materials are formed using different kind of nematogens and this kind of materials which can act as both smectogens and nematogens. So let me stop at this point. If you have any doubts in the discussion that we have, all the definitions that we discussed, right, nematogens, smectogens, nematic phase stability, nematic range, and monotropic versus enantiotropic behavior of this materials. So you just go through it. If you have any doubts, we can discuss that in the next class. Okay, so let us stop here for today and see you in the next class, hopefully on a live mode, so that we can have some discussions, live discussions, so that we can clarify our doubts. Okay, see you in the class. Bye bye.